Hello, everyone. I'm Garrett Womble, and thank you for joining. Today's presentation and discussion by PRAXIS3 Principal Brian Tanner is the last of our 6-part webinar series on the future of research libraries, and will focus on the ways that high-performance design can be applied to preservation, restoration, rehabilitation, and renewal projects. We appreciate the opportunity to answer any questions you may have following today's discussion. Those questions can be submitted throughout the presentation by using the dialog box on the right-hand side of your screen. And with that, I'll turn it over to Brian to get us started.
Thanks, Garrett. So the title this time is Preservation and Performance, High Performance Design Strategies for Renovation Projects. And we're really talking about preservation in the sense of preserving buildings and preventing them from getting knocked down to build new ones, more so than historic preservation in the traditional preservation, architectural preservation sense. So we're really talking about bringing high performance design to existing buildings when we renovate, renew, or preserve them. So let's get started. Here's the agenda. Renovation is the first step toward high performance. We're going to talk about that a little bit. We'll talk about the building envelope and some ways that we can approach performance with regard to the envelope, generally speaking. We'll talk a little bit about the energy model and how it's useful, how it can be useful in a renovation versus a new construction project. We're going to look at glazing. Single pane and insulating glass is always an issue that we run across when we're doing. It's one of the main battlegrounds of a renovation project is what to do with existing glazed openings. And then we'll talk a bit about material reuse and some opportunities and options for that. And if we have time, some questions at the end. So renovation, the first step toward high performance. It's often said that the most sustainable thing that one can do with a building is just not tear it down, find a way to use it. And it's hard to know when to renovate and when to build anew, particularly in a situation where you're trying to radically transform a building for a new generation of students, for example, or because its use is programmatically obsolete, or other things have happened across time that really, call out for a truly transformational project. How do we make the decision of when to tear down and when to build new? And these are hard things to do. One of the things that we've found, though, is that the best approach, once the owner has made that decision to renovate a project rather than knock it down, is to look for ways to work with the existing building as opposed to trying to work against it. And so here you see the building we were just looking at is a building at ABAC's campus, Tifton, Georgia. We look to sort of preserve as much of the bones of the project. You can see we've got an existing exterior stair that we're going to retain. We're keeping most of the brick wall, but we're doing some kind of surgical operations to the envelope in the image you see on the left. And in the interior, we've kept the structure. We've kept the structure of this existing atrium intact and taken out mostly just the partitions and the sort of non-structural elements to do a really radical renovation of the building, but working with what's there. One of the things we discovered when we took the existing ceiling panels down is how beautiful the concrete structure was, and so it actually gave us the opportunity to incorporate that as our finished material, and it really has a dramatic effect. And maybe some other time I'll share some images of that. But that was an example of working with what you've already got as opposed to tearing down something just to build something new. And it came out pretty well. We were able to create a new image for the building, one that the students, I think, have embraced and that the campus is happy with, and that it does give this building a fresh start without having to totally remake all aspects of the building. We're able to really give it a good reset. Hopefully it can serve for the next 40 or 50 years for that campus. So the envelope is where we end up operating a lot of the time, and we're going to talk about performance as it relates specifically to the building envelope. And so a lot of times with these buildings, especially brick ones, you're dealing with mass walls or walls that have little or no insulation in them. Oftentimes there's not an air cavity. Oftentimes there's not a weather barrier. All kinds of walls we come into contact with in the envelopes of these buildings built in the middle part of the 20th century. And in a project that we recently completed at Georgia Tech, that was precisely the case at Crosland Tower. Here you see a very early design diagram of our basic design approach for this building. The black lines you see are kind of solid masonry mass walls. So these are brick walls, no air cavity, grouted full, CMU backup wall, brick mass masonry wall. that was the condition on all four sides of the building originally. There were very few windows in this project, and our main sort of design approach was to open the building to the south and north by putting in glazing, which you see in the blue stripes. And where we face the south, we put in some sunshades to sort of protect that glazing. And at the north, we didn't have to do quite as much glare and solar gain management on the north side. But on the east and west facing walls of the building, we kept these existing big mass brick walls. And so the design team was asking itself, what do we do to improve the performance of those walls? We're going to be able to put in 21st century curtain walls on the north and south, but what about the east and west? So we started studying what those envelopes, what those walls could be like. And what you see in the first image on the top left is the exhibition. It's a brick veneer on a grout-filled, very narrow cavity. It's not really a cavity, it's just filled up with mortar and grout. And then CMU backup wall sitting on a concrete structure. It's actually not a concrete structure. It's actually a steel structure encased in concrete. It's a really weird building built in designed in the mid 60s. Is the existing condition that we were working with. One of the first things we investigated, naively I might add, was the introduction of some rigid insulation to the interior face of the wall that we could clad with chipboard and maybe improve the insulating value of that existing wall. Would have been a disastrous thing to do because it puts the dew point right in the middle of where that CMU backup wall is, and that creates all kinds of moisture problems. And it wasn't long before we figured out that was actually not a viable option. Another option we looked at was removing the brick, salvaging it, cleaning it up, putting on a continuous insulation barrier and weather barrier on the CMU backup wall, and then reinstalling the existing brick. Those of you that are property managers and facilities directors will know why we didn't choose this option. It would be very expensive to do this sort of thing, but we did investigate, at least from a constructional standpoint, what it would involve. We also looked similarly at using a metal cladding over a continuous insulation layer, much less labor intensive, but more material cost. We also looked at some options that really did more of a gut renovation, where we took down the CMU backup wall and the brick and really put in a new conventionally framed light gauge framing system with either continuous insulation and metal panel, or using a sandwich panel of metal and insulation that we could attach to the structure. These were more plausible, but they really didn't mesh with the sustainability goals of the project, which is to preserve as much of the material as we possibly could. So we looked at what we were doing for the curtain walls on the north and south face, which where we have glass, and we were getting considerable solar gain and a lot of radiation coming through the wall. We introduced those yellow boxes, which were areas where we were going to have sunshades to protect the glazing from direct light, that radiation and so forth. And we asked ourselves, what if we could do something like that in front of the brick? Would just doing that improve its performance? And the answer was yes, it would, but it would be a pretty complex thing to do. And we ultimately, you'll not be surprised to find out that what we ended up doing is keeping the existing wall, because the wall had been working pretty well for about 50 years. And in looking at the energy model, what we discovered was that most of the performance benefits that we got on this project, and they're pretty substantial, we'll look at those later, happened by how we treated the openings. And the needle wasn't moved very much by any of these things that we did to the solid envelope. It would improve this way or that, but when you compared that against all the embodied carbon that was in these existing walls and how well they were actually already performing, and if that we could get increased performance by improving the glazing systems, that we would stick with the existing wall. And when you do that, you just have to be mindful of the fact that we built walls differently in the 50s than we do in the 2020s. And on the left, you see an example of a 1950s detail with a mass wall where it's very permeable. Moisture can actually travel inside to outside pretty easily through this wall because there's no true weather barrier. And the only real barrier that we have is this layer of waterproofing flashing at each of the floor levels. But in new buildings, we put in a weather barrier that's a hard surface for moisture to rest against, go down through the air cavity, and then be weeped out of the wall. both these systems can work very well. Where you get into troubles when we try to combine them and say we do some selective demolition in an existing wall and try to put in the wall on the right into a small area of the wall on the left, and we mix and match and we start getting moisture trapped in the wall. So we want to be mindful of what we really have in place. So at that project, this is an image of the completed project that we've been looking at so far. We focused on the openings. We focused on high performance glazing. We focused on the solar heat gain properties of the glass. We shaded the glass where it faces to the south. We created these optimized sunshades that allow people to see through in the zone that corresponds to where most of our eyes are. And the angle of the louvers is different in other places to create maximum shading for the glass and also to reflect light back up to the ceiling at the interior of the space to increase the daylighting profile. So we really focused on those and kind of left the brick alone. It's kind of the lesson we learned on that project. And here's the Carlton Center that we looked at earlier from a different angle. And you can see that we've got, this is an east facing facade. So this vertical sunshades help us in that kind of mid to late morning when the sun is kind of moving around toward the left of the image, and creates some learning spaces behind that get really nice diffuse light for most of the school day. And it's a really, really nice space. And it's actually by focusing on that area as opposed to all of those brick areas, we were able to get not only some good energy performance, but also some quality of life performance there. So we talked about energy modeling a little bit earlier. When we say the real baseline, what do we mean by that? When we do energy modeling, most of the time we're well, that's what an energy model is. We compare the design that we're working on right now, which is what you see described in these data points here, against an abstract baseline project based on the ASHRAE standard. So this is an abstract idea of what a typical project would be, and then we're measuring the performance of our actual project against that hypothetical project. But when you're doing a renovation, it's not a hypothetical project. You have an actual building that you've been owning, operating, and paying bills on for 40, 50, 60, 70 years. And we can do an energy model of the existing building and get an actual understanding of what its EUI is. And then, so then when you're comparing the design EUI to your actual EUI from your existing building, you get a better understanding of the real kind of improvement in cost and performance that you're getting compared to your existing asset. So it can be counterintuitive. Some people think, oh, why would I do an energy model? It's a renovation. I don't have as many options to change things. It's not going to really move the needle. Actually, it has the opportunity to move the needle more because you really can compare your existing sort of profile. And this building was a pretty good success story. And I know some of you all have heard me talk about this before, but I'm going to do it again. It's we doubled the seat count of the library. We have twice as many people are able to use the library as it was in its existing condition, but reduced its energy consumption by 6%. So twice as many people served, 60% less energy required to serve them. That's a pretty amazing thing to understand when you really want to know how your buildings are performing. Here's another example at our Carlton Center project. Also, a library was a component of this project, where we use the Cove tool, which we use kind of early in the process, but we also use it retroactively to measure certain moves that we're making. And we did the same thing. We created a model of our existing condition and a model of our new condition, and compared the performance of the two. You can see our EUI was able to improve from 48 to around 30. That's a 17 improvement of 17 in EUI. Our CO2 reduction was improved from 55 to 72%, which the higher the number for that, the better. And then for our water use intensity, we have a lot more users in the building than we had in the original building. So our overall water usage is up, but you can see that our water use efficiency is improved from 46 to 14. Those are pretty radical moves, and it's not just compared to a baseline, but compared to the actual, the building that we can model in there, we found to be pretty helpful. Next subject, glazing. So we talked earlier on the Georgia Tech Library project about, well, on both ABAC and the library, about glazing, and it is one of the main battlegrounds, especially for mid-century buildings, which inevitably have some single pane glazing that is probably a character defining aspect of the original building's design, and therefore something that needs to be treated with some delicacy and respect, but which also is your primary place where you can really improve performance from an energy standpoint to make a high performance building. On the left, you see a typical sort of aluminum window, single glazed. It's direct. The single pane is direct glazed into the very light frame. On the right, you see a sample of an insulating glass unit. So it's the thickness of the thing that makes it work. The fact that there's two pieces of glass and an airspace in the middle and some other coatings are what create the high performance of that glazing. So it would seem to be simple. You just put the thing in the right into the frame on the left, and it works, and we all move on with our lives. But it is a little bit more complicated than that, and there are also a lot more opportunities than that to operate on existing conditions like this. The first of them is to use an interior storm window. It's very much like a storm window that you may have had on your house growing up, except it's on the inside instead of the outside, and it's manufactured and designed specifically for this kind of purpose. It simply creates an airspace between the pane of glass of the storm window and the pane of glass in the existing window to get the insulating properties. It's affordable, it's less invasive, it doesn't break apart the weatherproofing around the window, it preserves the historicity of the existing window, if that's something important, and it preserves the historicity of the glass itself. Sometimes we're looking at buildings that have glass that has some historic properties to them. This allows those things to remain in place. So it's affordable, and it can be an option. You can mount it behind the frame as shown in this detail, or there is an alternate mounting location. Depending on what type of frame you have, you can put it directly behind the glass if depending on what your architectural goals and priorities are for the project. So a good solution is to use an interior storm window. One can also do what we talked about before, taking an insulating glass unit and simply replacing the single pane glass with an insulating glass unit. This only works if the frame is big enough to receive it. So if the whole idea of insulating glass has to do with the thickness of that unit, your frame has to be thick enough to receive that piece of glass, and that's not always the case. Those IGUs are generally probably the smallest one you're going to get is probably 5/8 of an inch, usually more like an inch. So this is not always possible. This is a little more expensive usually than the storm window option, but the benefit is similarly, you're able to keep the frame in place. You don't have to, it's not invasive. You don't have to break the frame apart. It's essentially not a whole lot more complicated than replacing a broken pane, just with a more expensive and higher performing piece of glass. A third option is to take the window unit and remove it altogether, take it to a shop, have it refinished and reglazed in the shop, and then reinstalled as if it's a new window in its existing this is more expensive than the previous two we looked at. The main benefits you get out of this are if the frame itself has some damage, if it's got some weathering damage or some corrosion or other things like that, those can be addressed in the shop. It can be recoated. It can be, depending on how it's built, it may be able to be reanodized or powder coated or some other type of finish applied to it. It can be glazed under controlled conditions in the shop and then brought out and installed in a really efficient way. Downsides to this one, it's expensive. It does require you to reset the window in the opening, so there's some waterproofing things that have to be dealt with. The advantages are, though, a lot more control over the craftsmanship and the look of how the window ultimately looks if you really have to make big transformations to the window itself. So here's an example of that. We did this third option on this project. This is Decatur Recreation Center in Decatur, Georgia. These windows look great. They look like they did in 1951 when this building was done, and they perform at a much higher level. And we were able to increase the performance of this project. Here's a building we did for Georgia State where we had some steel windows. This was a building that was a parking deck and was in quasi-abandoned state for a little while before Georgia State took it over. The windows had to be replaced, but we were able to find windows that matched the sort of profile of the existing ones and worked with that. This is a project at Georgia Tech where this is actually the third window system that's been installed on this building. The original one was milled aluminum custom shapes, single glaze, direct glaze to those custom shapes. So it wasn't a storefront or curtain wall in the sense that we speak of it today. And architecturally, it was beautiful. Performance-wise, it was miserable. It did not do a very good job in any way in terms of energy and comfort. In the 90s, this curtain wall was replaced with a 90s era curtain wall system, a sort of traditional Conair type 1600 curtain wall system with insulating glass, which performed better, but did not have the, architecturally speaking, it did not have the subtlety that the original design had. It didn't have any hierarchy between the width of verticals and horizontals. And there were some subtle things that really didn't do service to the original design, the 1953 design of the building. And some of the IG units had become cloudy. We were going to have to replace a bunch of the IG units anyway. So the decision was made to replace this with a 21st century curtain wall, but using the 1953 design as our basis. So we have a little bit more fidelity to the building's original intent, even though this is not a truly new, even though this is a new curtain wall, which is the fourth option that I didn't present here, which when you're going to address an existing single pane glazed window, you can just take the thing out and replace it with a new window, if that's really what you want to do, which is what happened in this case. So it's lots of options for glazing in these buildings. Lastly, I'm looking at the time, I think we're okay. Material reuse. So in following up on the idea that keeping an existing building is really the most sustainable thing you can do versus new construction, material reuse, both on-site and saving materials for reuse elsewhere, is also a really profound way to keep our carbon footprint down in our construction activities. And these are some images from the Lifecycle Business Center website that show examples of the types of products that can be either salvaged for reuse in the specific project they are salvaged from, or materials that can be salvaged for reuse by others elsewhere, or materials that can be obtained and used in a renovation design of the building that you're working on. These are incredible resources that really upcycle these materials for new use. And it's better than recycling because they're not being ground up and using carbon to ground them up and use other purposes. If we can actually leverage the actual material into a new use or a new configuration. So this is everything from countertops to lumber to trusses, all manner of doors, some of them using very fine materials and rare woods and really high quality craftsmanship, even grills and registers, and then paving stones. When we try to reuse brick from an existing wall that we take down and reuse the brick somewhere else, it's a very labor intensive thing to remove the mortar from the brick so that it can be relaid. In fact, I'm told by the masons that when we do that, about a third of the brick can be actually reused in the new building. About 2/3 of it are lost just in the process of trying to knock all the mortar off the brick. So one advantage of upcycling pavers is that oftentimes they're loose laid or sand in a sand bed, and those can be taken out and very easily reused in another situation. Big fans of the Lifecycle Business Center. PRAXIS3 are sponsors of the Lifecycle Building Center. And this is not at all a shameless plug. I have no shame whatsoever in plugging what they do. I think they're an incredible organization. And if nothing else, it's fun to go there and check out all the stuff that they have. So if you haven't done that, I encourage everybody to engage with Lifecycle Business Center for ideas and opportunities about material reuse in all of our projects. Just here's some examples of some projects. This is the Decatur Recreation Center. The wood paneling you see above the fireplace there, and also on the right-hand side, some wood panels here and also on the ceiling. These are upcycled from the space immediately to the right of this one was formerly a gymnasium with some folding bleachers, and they were wood folding bleachers. And these are those bleachers, and we refinished them, got them stained, and converted them into a really nice cladding material, which is one of the things that, the community has embraced most about this building, is the way that history connection exists in the design. Plus it feels nice and looks good. Similarly, a project that we just finished construction documents for at Georgia Southern's Armstrong campus, we're converting another gymnasium. There's a gymnasium theme here today, Garrett. Another gymnasium, pre-engineered metal building, volleyball, competitive intercollegiate volleyball gymnasium that we're converting into a student success center, and we needed to remove some sections of the existing hardwood floor, and we're recycling the hardwood strips, and we're going to use them as cladding on this wall behind the lobby desk, and also in the student success kind of collaboration areas is where peer-to-peer tutoring will happen, some offices for advisement and project rooms and collaboration amongst the students, and a little mezzanine here for other kinds of group study and collaboration. And we're using the wood we're upcycling the wood to use for cladding in that space. And then at the Georgia Tech Library, we did, because we looked at those diagrams where we were tearing off the brick on the north and south facades, we did salvage all that brick for reuse, because you need lots of brick to finish out all of these edges where we're inserting new windows, and there's always point up and repair and things that have to be done, and using the existing brick to match the existing brick is always a better option, architecturally speaking. We also, because this is a high-rise building and we had to do extensive code upgrades for this project, we had to install larger cabs, larger elevator cabs, and that came along with a higher override height than the original building would allow for. So this penthouse had to be extended upward quite a bit in order to make this project work. And so by salvaging the brick and reusing it, we were able to accomplish that in a way that this truly beautiful 1960s era brick we have fidelity to that finish across the entirety of the renewed project. It was a lot of work. I'm not going to lie to anyone and say that it saved any money to save that brick. In fact, it probably ended up costing about the same as all new brick would have cost. But we were able to keep that material on site and keep that carbon inside the footprint of what we were doing there at Georgia Tech, which was one of the stated goals of the project. So conclusions, real quick. By choosing to renovate or renew, we're already engaging in high performance design. It's one of the best things we can possibly do. When we're dealing with an envelope, racking up R value points in walls isn't necessarily the most impactful way to increase a building's performance. We've typically found that focusing on openings is the most highest impact in a renovation scenario rather than re-engineering existing exterior walls. A small early investment in a robust energy model can pay big dividends in the end, both in terms of performance and project cost, and that's literal cost. We can hopefully find ways to save money for the next 50 years of a building's life by understanding via the energy model what we're able to achieve. There are multiple ways to improve insulating properties of existing glazed openings, and we looked at a lot of those. And also that reusing or adapting existing materials on site will reduce a project's carbon profile, but also preserves a tangible connection with the building's history. And that's really the point I want to end on, Garrett, is that all of these things make sense from a performance standpoint when we talk about energy or water or carbon, but they also create an actual tangible connection to a building's past, which if we want these buildings to survive and be sustainable in the future, people have to love them. And one of the best ways to make sure they love them is to retain part of what they may have loved in the first place. And reusing materials in an exciting and fresh way is one of the best ways we can do that. It's really a win proposition. So I think that's all we had today.
That's it. Thank you so much, Brian. It's been such a great series, and this topic in particular, something that we're dealing with on so many of our projects. And I'd encourage anyone that missed a segment along the way of the 6-part series here to please take a look at that either on our website or any of your favorite popular video channels. And thanks for taking the time to meet with us. And again, thanks to Brian for putting this together and leading us through it. And we will talk with you all soon.